Example F wants us to find the solutions to 4 times sine of x times cosine of x is equal to the square root of 3. And our hint here is to use the double angle identities. So I can rewrite the left-hand side as 2 times 2 times sine of x cosine of x is equal to the square root of 3. And hopefully this thing here looks familiar because that is the double angle identity for sine. So we can substitute that for sine of 2x. And now what we can do is we can divide both sides by 2 to get rid of this, and we get sine of 2x is equal to root 3 over 2. So I'm going to go ahead and draw my unit circle, and there are 2 locations where the sine value is equal to root 3 over 2 on the unit circle. And we know that sine is positive in quadrants 1 and quadrants 2. So the first angle we have here is equal to pi over 3. And then the second angle that we have here is 2 pi over 3. So this example is a little bit different than previous examples because the interior angle here inside of the parentheses is not just x or theta. In this case, it's 2x. And so normally I would write x is equal to pi over 3 plus 2 pi k, where k is an integer, and x equals 2 pi over 3 plus 2 pi k, where k is an integer. However, what we did was we found that 2x was equal to sine inverse of root 3 over 2. And so now we have that 2x is equal to both of these things. And so things are going to be a little bit different in that I need to solve these for x. And so I have to divide both sides by 2. And so what does that end up looking like? Well, on the left-hand side of both of these equations, the 2's will divide out. And what is that going to leave us with as far as a final solution? So here, I need to divide pi over 3 by 2, and I also need to divide this by 2 as well. And so if I do that, that's going to end up giving me pi over 6 plus pi k, where k is an integer. And then my second part of my solution is going to be pi over 3, because 2 pi over 3 divided by 2 gives us pi over 3, and then we also need to divide the 2 pi k by 2, and that's going to give us pi k. And that will be our final answer for this example. Example G says tangent of x plus the square root of 3 is equal to secant of x. The hint tells us to square both sides and to use identities. In this case, we might have created more solutions, therefore we want to check our final answers to eliminate the wrong answers. And sometimes that happens when you square both sides as a technique of solving these. So we have tangent of x plus the square root of 3. We want to square that, and then we want to square the right-hand side as well. So for the left-hand side, we're going to have to FOIL that. So I'm going to write this out to help me. Okay, so first, outer inner and then last. And secant squared x on the right-hand side, we can manipulate that so that we can change that using the Pythagorean identity. So let's combine like terms on the right-hand side. So we have tangent squared x plus 2 root 3 tangent x plus 3 is equal to, and then the right-hand side is equal to tangent squared x plus 1 from one of the Pythagorean identities. Now what we can do is we can subtract tangent squared x from both sides. So if we do that, then these will cancel out. And then I can also subtract 3 on both sides. And if I do that, I get 2 root 3 times tangent of x is equal to 1 minus 3 is negative 2. Now, as I'm working through this, I'm realizing something that I want to mention is that this is not a trig proof. We are not proving a trig identity here. What we're doing is we're solving for an x value that makes this equation true, which is what allows us to work with both sides of the equation. When you are doing a trig proof, you cannot work with both sides of the equation. The best thing to do is to start with one side and manipulate it so that it ends up looking like the other side. So it's very much not like solving an equation. Solving an equation, you can work with both sides of the equation. When you're doing a trig proof, you want to only start off with one side of the equation and then manipulate it so that it looks like the other side. And that is a very important difference. So back to this example, I now want to divide both sides by 2 times the square root of 3. So those will divide, and we'll get tangent of x is equal to, these 2's will divide, and we'll be left with negative 1 over the square root of 3, which is the same thing as negative root 3 over 3. So now, if I apply tangent inverse to both sides, we get x is equal to tan inverse of negative root 3 over 3. And this is actually one of the values that we get from one of the common angles on our unit circle. So I'm going to come up here, and tan inverse of negative root 3 over 3 is equal to negative pi over 6. And then we need to think about what angle we're going to add so that we can hit all of the correct locations. And so I'm just going to sketch a really quick graph of the two functions that we're looking at. So the first one on the right-hand side is secant of x, and so that is the reciprocal of cosine. So I'm just going to sketch cosine. And cosine looks something like that. And I know that cosine is 0 at pi over 2 and 3 pi over 2, which is also the location of the vertical asymptotes for tangent. Okay, so secant looks something like that. And then tangent I'll graph in another color, but remember we're graphing tangent of x plus the square root of 3, so that ends up being a vertical shift. And so it's going to look something like that. And so we have located this value, the x value where they intersect is negative pi over 6. And then where is that intersection going to happen again? It's going to happen here, and we know that the distance between here and here is 2 pi because that is the period of our secant function. So that tells us that we'll have x equals negative pi over 6 plus 2 pi k, where k is an integer. And that concludes this example.